Okay, today we're going to be talking about Chapter 3, Section 6, Fluid Displacement. So fluid displacement applies to any fluid, either a gas or a liquid. Both are fluids. And we're going to go way back in time to the ancient Greeks, to a man named Archimedes. And Archimedes made some key discoveries about buoyancy. Actually stemmed from, you can read about this in your book, a challenge given to him by a king to figure out if a crown that he had made was made of gold or some other metal. And when thinking about this, he got into a bathtub. So if we imagine a bathtub full of water, so it had water in it, Archimedes got into the bathtub, and when he was in the bathtub, the water spilled out. And he had an aha moment. Aha, says Archimedes. The volume of water I displace is my volume. This aha made him realize he could weigh the crown with a scale, and then he could put the crown into a full container and measuring the amount of water that flowed out, and then find its volume. And then knowing its weight, or mass, is the more technical term that we would want to think about, to its volume would tell you its density. Okay? Another thing that Archimedes noticed is if you put the crown or any other object into water, we submerge it into water and attach a scale, the object weighs less in water. This got him thinking as well, and he began to realize that this weight loss was due to buoyancy. Buoyancy is a hard thing to spell. It's like buoy, which is the tendency for a solid object to float when put into a fluid. So the principle of buoyancy he discovered is that the force, the buoyancy force, equals the weight of fluid displaced. This is true for any fluid, not just water. So the buoyancy force equals the weight of fluid displaced. That is, if we take an object, like a boat, and submerge it in water, the boat has a weight of some amount that's pulling it down to the ground. There's a buoyancy force also pushing up on the boat. And this is due to the amount of water that would have been here. So you can imagine the water that would have been here has been displaced. So the weight of all that water is the amount of force pushing up. That's what Archimedes discovered. So let's do an example problem of this fluid displacement. A certain wooden box is 1 cubic foot in volume. So if we imagine a box, box is a cube. I think we should have said that here. A certain cubic wooden box is 1 cubic foot in volume. We're going to need to know that to do the problem. So if the cubic box is 1 cubic foot in volume, then all of its dimensions are 1 foot. So this box is a cube, and it's 1 foot by 1 foot by 1 foot cube to make a box. And it's open on the inside, we'll imagine, made of wood. And so hopefully it'll float in some water. How much would the box sink in the water? So if we put the box in some water, how deep does it sink? Given the specific weight of water is 62.43 pounds per cubic foot. So we have to think about this a bit. We have to remember Archimedes' principle. The amount of water that we displaced, that weight will be the buoyancy force. Okay? So when we are floating, we're in a state of equilibrium, meaning that the amount of force pushing down on the box, which is 10 pounds weight, will equal the buoyancy force, 10 pounds pushing up. That's why it's just sitting here floating in the water. Assume the water is real still and the box is just floating. Okay? So you have 10 pounds pushing down, 10 pounds pushing up, which means 10 pounds of water must have been displaced. So we have this is the cross section, but if you imagine here this box, if this is the line we float at, we're going to have this area, this volume of water that we displaced. The weight of that volume of water is the force. So the force we know should be 10 pounds to equal the 10 pounds of weight. And we're told that specific weight of water is something pounds per cubic foot, 62.43 pounds per cubic foot. So the volume we can find as being this unknown height, maybe instead of x for our unknown, we'll use a d for depth. So the depth here that it sinks, this depth that the box sinks, that depth will be this force, 10 pounds. So we'll have the volume of water. So the volume of water will be, so we need to find first is the volume of water we displaced would be 1 foot, because the volume of a rectangular prism is the base times the width times the length times the height, basically. So we have 1 for our width, 1 for our length, and this unknown d is our height. So our volume is equal to d, this depth. And that's because I chose a box that's got these nice simple dimensions of 1 by 1. So we'll have a volume. So the buoyancy force, actually let's do F, force for buoyancy, F sub B, would be equal to the volume, well, it's equal to the weight of the water that's displaced. And the weight is going to be the volume times the density, or the specific weight in this case, is the way we'll find that. So the volume times the specific weight. Okay? So the volume here is d by our little equation over here. We sunk d feet in, and our specific weight was given to us as 62.43 pounds per cubic foot. So the units of volume are cubic feet. So if we imagine the units here, we'd have the volume is cubic feet, and the specific weight is pounds per cubic foot. We can write cubic foot faster like this. As feet cubed. Okay, and if we think about the units, these feet cubes will cancel, we'll be left with just pounds when we do this multiplication, which will be our force. So then we can write this equation, 10 is the depth that we sink times this specific weight of water. And since waters are fluid, we wanted to know the weight of that water to find the buoyant force. We know the buoyant force has to be 10 to match the weight of the box to figure out where it sinks and stays put. So then we need to use a calculator to find the answer to this. So let's pull up our trusty calculator, wherever we get a calculator from. And we see that we need to divide, in order to solve this equation, divide both sides by 62.43, be the depth. So that would be equal to 10 divided by 62.43, 0.16 0.02 feet. Now, this is a technically correct answer, but who thinks in 0.16 of feet? Let's turn that into inches. So let's find our calculator again that I lost. So to find it in inches, we just need to multiply the number of feet by 12 to get inches, since there's 12 inches in a foot. And that gives us 1.922, or about 2 inches. About 2 inches. Okay. That's not very far when we had a 1 foot side. So if you think of the side of the box being 1 foot, we only sunk in 2 inches, or about 1/6 of the way down, 0.16. So that's the answer to A. So now if we add 30 pounds of weight to the box, how much will the box sink? So if we put in some weights into the box and make it weigh more, so maybe we'll throw in a kettlebell or something that weighs a lot. Just a big iron mass. Okay. Now the box is going to sink further into the water because it weighs more. This depth will get bigger. We have 40 total pounds pulling down the box, and then once it settles down and quits moving, we have 40 pounds of buoyancy force pushing up. So now our equation becomes 40 is this unknown distance times our specific weight of water is the same. So we can leave that alone, and then we don't have to worry about any more other changes to this equation. We can just solve 40, excuse me, I don't want it to be that big. Let's change there we go. 40 divided by 62.43 will be our depth that we sunk. Get the calculator back. 40 divided by 62.43 is 0.6407. 0.6407 feet. And again, don't know about you, but that doesn't mean a lot to me. So if I multiply that by 12 to get inches, 7.689 inches deep. So more than halfway. Part C, how much weight would need to be put into the box to make it completely submerge into the water? Okay, so if we think about this setup, if we completely submerge the box into the water, how much weight needs to be added? So first of all, how much would it weigh? Well, it's going to weigh whatever the buoyant force pushing up is. And the buoyant force pushing up would be equal to the weight of the amount of volume of water we displaced. Well, here we displaced an entire cubic foot of water, and 1 cubic foot of water weighs 62.43 pounds. So we know the buoyant force would be 62.43 pounds pulling up on the box. Well, if it's sitting still, then that has to be its weight. And since it has to weigh, let me erase this real quick. Since it has to weigh the 62.43, we know that the total weight then would be of what we added to the box would have to be 62.43 pounds minus the 10 pounds the box weighs. But so that's how much weight we add. So the box weighed 10 pounds by itself. We have to put in 52.43 pounds of weight into it to make it completely submerge into the water. And of course, in reality, if we did this, some water will spill over, and then adding more water into the box will make it weigh more, and now it's going to sink all the way and just sink into the bottom of the sea, so to speak. So the book goes through lots of examples of applications of how this principle works. And I'm not going to repeat all that. Please read the section in your book. But I wanted to go over an example of how to apply the principle mathematically, because there will be some questions about that in an upcoming quiz or homework assignment, I'm sure.